Welcome back. And congratulations, you've made it through recurrence relations, rules, sequences, VNs, N-1s, TNs, and so on and so on and so on. It's a lot, isn't it? Well, now we need to start applying it to the real world, which is financial maths. Now, you remember I did mention we have to be careful with the difference between a number sequence and a financial number sequence. So this is going to go through where the changes happen and the things that are slightly different. And yes, I will give you a big summary page at the end so you can copy all the formulas down. All right, ready? Let's go. Bit of revision first. Number sequences. Okay, 1, 3, 9, 27 is an example of a number sequence. So we can have recurrence relations, and of course they allow you to find all the values in a number sequence. Okay, we have two types of number sequences: arithmetic recurrence relations, or arithmetic sequences, and this one's the recurrence relation which applies to an arithmetic sequence. Or we have a geometric recurrence relation, which of course is the T0 equals the start value, next value equals the common ratio times the current value. Have a look at this one up here. How do we get from 1 to 3? Plus 2, so it's not arithmetic. 1 times 3 is 3, times 3 is 9, times 3 is 27. So it is a geometric recurrence relation, which applies to that sequence. All right. As well as the recurrence relations, we have the rules, which allow us to only find the nth value. So we could just plug it into a rule, say we want the 20th term, rather than going enter, we could just plug it in the T20 into the rule and find out what the value is. The arithmetic rule looks like T0 plus n-1 times d, and the geometric rule, which is for this one, would be r to the power of n-1 times T0. Now, again, T20, we would type in r, which is 3, we worked it out, to the power of 20 minus 1 is 19, times our initial term, which was 1. Right. Have you ever wondered, though, why we start a sequence at T0 rather than T1? I'm glad you asked. It's mostly to do with financial maths and financial math sequences. So let's have a look at the difference, the basics, financial sequences. Now let's say you have $5,000 to invest in a bank that offers you 2% per annum interest paid monthly. What the bank does at the end, it's online now, but what they used to do is send you a monthly statement. Now that statement has a name. It's called an amortisation table. All right, at the end of every year, now this is 1 year's worth of this, they would send you a breakdown of how much interest you earned every month and what the balance was at the end of every month. So in this case, $5,000 was invested, 2% interest calculated on that balance gave you $8.33. Be careful, it's 2% per annum paid monthly. So it's not 2%, it's 2 over 12, isn't it? So it's 1/6% each month. Goes all the way through there and ends up with $5,100.92. Now, what this means is this your first month here, or is that your initial balance? Did you earn any interest when you put the money as soon as you put it in there? No, you earned the money at the end of the first month. So the initial balance of the term is V0. Even though it's the first number in the sequence, it's V0. You haven't earned any interest, and that's where the difference is. It's all about the interest. The balance after the first interest payment is V1. The second is going to be, of course, V2, and so on. Okay? So it comes all the way down. So by the end of it, you've earned 12 months worth of interest. So when you're dealing with financial stuff, you are really only interested in the interest paid for the year, the 12 monthly interest payments, not the initial balance, which is why we start with V0. In a number sequence, though, that would be, you could think that as the first term, if it was just straight numbers. When reality is This is the one we're interested in, the value. Now you notice I've said V0 here. That's a simple thing I like to do so I can differentiate between a number sequence where I use term numbers and value of an investment, which is to do with financial. T for numbers, V for value and financial. All right, let's have a look at the similarities and differences. So number sequences, we have an arithmetic recurrence relation. We have an arithmetic rule. But financial number sequences, we have arithmetic, which is simple interest equals simple interest. Remember that, simple interest. Simple interest, it's a set amount each time, and arithmetic goes up by a set amount each time, doesn't it? Does that look any different? No, it doesn't. Apart from the V's, V0 equals A, Vn plus 1, so the next value equals the current value plus a common difference. Now, that common difference is the amount of interest you get paid each time. And that's only calculated once. Think back, what was your simple interest formula? What was it? It was I equals PRT over 100, correct. Learned that back in year 7, back at the start of high school. Now, I isn't D, but it's the same formula. What was P? P was the principal, the start value, wasn't it? Which was V0. R was the interest rate, and T was the amount of time. Now, that could be broken up into months, for example, 1 over 12. It is the same formula that we use, but we write it with a D. V0 equals R, V0 times R over 100N. R is the interest rate, V0 is your initial balance, and 100N, N is the number of payments, number of times interest is paid per year. Okay, that's the only extra bit we have to do with financial. Otherwise, the recurrence relation is exactly the same. What about the rule, though? See any differences there? I do. Look at that. N and N minus 1. Again, arithmetic number sequence, we need to include the first term, but that's taken care of there. With financial, we don't need to include the first term because it's there and included. Okay? We're only interested at the end of the first month. We don't need the first value in there. So, here it is, the summary. Financial sequences don't have to worry about the initial value. Don't worry, we're going to get through some examples and hopefully that'll help explain things. And again, I will put the summary at the end of the show. Geometric sequences, what were they? R times Tn was the recurrence relation. R to the power of n minus 1 was the rule. So at geometric, arithmetic is simple interest. You guessed it, geometric is compound interest. So again, the recurrence relation is the same. What do you think the rule is going to look like? Is it going to have R to the power of n minus 1? Nope, just R to the power of n. Now, R we have to work out, just like we had to work out D up here. This R we don't know. You might be told it, you might be lucky, but if you're not told it, you have to work it out. So here's a formula. R equals 1 plus little r, the interest rate, over 100n. The interest rate over n being the number of times interest is paid per year. Ready for some examples? We're going two or three lots of examples. First one, simple interest. Good old Bob. Bob had $2.5 grand in a bank account, which pays 0.5% simple interest per annum. He doesn't have any money of his own. Calculate the balance of the account for each of the first 4 years and calculate the balance of the account at the end of the 20th year. Now, there's two things going on here. One, we need to work each of the first 4 years out. So that means we have to use a recurrence relation for part 1, and we want the 20th. We could use a recurrence relation for that, to work out the 20th year. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, sorry, what was that? Oh, what was I up to? Yes, you know what I mean. We use the rule to work out the 20th year. So first up, our initial value, $2,500. So that's V0. What do we have to do next? We have to work out what type of recurrence relation we want to use. Simple interest. Now that is an arithmetic financial sequence. Okay, write down the recurrence relation, Vn plus D. Are we told D anywhere in the equation? No, we just know the interest rate. So we have to work out the equation. Did I say equation? I meant question. In the question, we're only told the interest rate, which is 0.5% per annum. Okay, that's not very much, is it? So we need to work out what the D is. R is 0.5, so D, there's our equation. Don't worry if you didn't write it down. I'm going to give it to you. Just sit back and relax and watch. V0, what was our V0? $2,500. R was 0.5%. N, now it's only per annum, which means once per year. So that's just 2,500 times 0.5 over 100 times 1, which gives us $12.50 interest each year. We can substitute that and that into our formula there, and we have our final simple interest recurrence relation. Now, to work out the first 4 years, grab your calculators. Now, CAS or ClassPad, use them. Much better than using your scientific because you don't have to write down the value each time. So you press 2,500 and press enter, and it comes up with 2,500. Next line, that's your V0, that's your initial amount. You've initialized your calculator. Press plus 12.5 and then enter, and it comes up with V1. Then you press enter, 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 and it comes up with V2, V3, and V4, which is 2,550. End of first year, end of second year, end of third year, end of fourth year, and of course, you finish off with after 4 years, Bob has that amount of money, $2,550. Looks the same as the stuff we've already done. Let's do part 2, the balance after the 20th year. So we use the rule, which was Vn equals that. We've already worked out the important bits. We've worked out the D. So N's 20, 2,500 for V0, and D is 12.5. Sub it in. There we go. And 20 times 12.5 is, of course, 250. So he has $2,750 in his account after 20 years. Great, nice. Straightforward, simple interest. Let's have a look at Sue now. Sue has the same amount of money. She puts in the bank, which pays 0.3, so less interest. But it's compound interest this time per annum. No money of her own, and we're going to work out the 2 parts, end of each of the first 4 years and after the end of the 20th year. So $2,500 goes in, that's V0. Then we have compound interest. So what does that mean? That means compound interest is a geometric financial sequence. Write the sequence, the recurrence relation down, which is what we need. Do we know the R yet? The big R? The common ratio? No, we don't. We know the interest rate up here, not the common ratio. We just know the interest rate. Don't mistake little r up here for this R. This is the interest rate. That's little r. We need to work out big R. So again, it's 0.3 over 100 times N. What was N? N was per annum, just once per year. So there we go, 0.3 over that is 1.003. Now we've got all we need. Substitute in 2,500, 1.03 times Vn. Using a calculator, first 4 years. Again, 2,500, press enter. Now times 1.003 is 2,507.5. And then enter, enter, enter. Again, you get V2, V3, and V4, which is $2,530. So you can see she's ended up with, from memory, a little bit more than Bob. No, it wasn't, because it was much lower interest rate. He was 2,550, wasn't he? Don't mind me. Finish it off with a statement. All right, let's see. After 20 years, we're going to use the rule again. So write the rule. There it is. Substitute the bits we know. Straight in, V20 equals 1.003 to the power of 20 times 2,500 is, of course, 2,600 now. This is where you have to be careful too. Notice how I haven't rounded there. You have to be very careful with your roundings. Remember, financial maths is always to 2 decimal places. Okay? Play it safe. Write a whole whack of numbers over here, the decimal places here, and then round it. Don't make the mistake of going straight from the calculator to the calculator and writing 0.34 or something awkward, or 0.36 by stuffing it up. Write it down first. You're less likely to make a mistake. And finish it off with a sentence. All right. Good so far? Simple interest, compound interest. Let's just plug it in formulas. All right, David. Now let's see what happens to David. He's got 3 different options. 1% compound interest per annum over different time periods. Okay. Here it is, over different time periods. He does not add any into the account. Compare the amount in David's account after 3 years when the interest is compounded annually, monthly, or weekly. Now let's see what happens. It's compounded. We've got an initial amount, so it's 2,500. So our V0 is 2,500. It's compound interest. So that means we need to use the geometric financial sequence. Do we need a geometric financial sequence? Hang on, we compare the amount after 3 years. So we're not going to sit there and go annually and go 1, 2, 3. If it's monthly for 3 years, how many times would you have to press enter if you use the sequence? 36, 12 threes. And weekly, 3 by 52, 156 times you'd have to press enter. No, let's use the geometric financial rule. Much quicker. We just do 3 calculations instead of that many. All right, so we're going to use the rule. Vn equals r to the power of n times V0. Now, do we know r? We're going to work, the r is going to be different for each one, isn't it? So 1% was the interest rate. What was r? 1 plus a little r over 100n. Okay, so this n is the number of times interest is compounded per year. This n up here, what n is that? That n is the number of times interest is paid in total. Now, I've done red and blue for a reason here. You'll see why shortly. This is the one you've got to be careful of. This happens a lot in year 12. If you can get it in year 11, beautiful, done. It will become second nature by year 12. Let's have a look at the first one. Annually, once per year. So R equals, it's once per year. So the little n down here is going to be 1. It was 1% over 1. 100 times 1, which is 1.01. So that means 3 years of annual interest. Okay, 3 years of annual interest. So what V are we going to, V what? V 3 times 1. Which means we're going to have 1.01, which is our R, to the power of 3 times $2,500, which of course is $2,575.75. Straightforward. 3 years, 3 payments, so 3 times 1. 3 years and 1 payment per year. Let's have a look at monthly. So we have to do the R again. We have to change the R. So what does the little n become over here? That becomes 12 because it's monthly, 12 months of the year, which works out to be 1.000083, sorry. All right. Now we have 3 years of monthly payments of interest. So how many? Not V3 anymore. 3 years of monthly, 3 times 12 is V3 times 12, which is 1.083 to the power of 36, because it's 36 payments. Does that make sense? Good. Which gives us $2,575.80. So even though it's paid monthly, he's got an extra 5 cents interest compared to over here. What do you think is going to happen weekly? Let's have a look. Weekly, R again, 100 times 52, because it's weekly, 52 weeks in a year, which gives us 1.0000, done it again, 192. Now 3 years of weekly interest, which gives us V. Now here I wrote 3 times 12, here I wrote 3 times 1, so here I'm going to write the 3 times 52. There's 1.0000, not 192, to the power of 156 times 250 times our initial balance, which gives us, yep, it gives us more money again, an extra 21 cents on top of the monthly. All right. Does that sort of make sense? So you have to work out the D first. If you're not told what the D is, you have to work out the R first if you're not told what the R is. And be careful of the weekly, monthly, fortnightly, biannually. There's all sorts of things. It's all about the number of payments per year. All right. Now, a couple more bits. Important words to look for. That's what we're going to look for. Going to look for, going to say, going to look for lots of things. Biannually, weekly. Not all investments go up in value. It's one of the things we're going to have to watch out for. Words like profit or loss. When we buy things, the value almost always goes down. Almost always. You buy a car for $50,000. You drive it off the car yard. It's now worth $40,000. Unless it's an electric car at the moment, but we'll see how that goes. All right. Which can actually be really useful at tax time, though, because you can claim what's called depreciation. It's also known as decay, if you're talking in terms of real life things. All right. Arithmetic, the word arithmetic, words you're looking for. Simple interest. If investments go up, there are some subtle changes here. Your equations look like plus D, where D is that. If investments go down, though, now this is plus, it's going to be plus D, investment's going to go down. What's that going to turn into? Minus D. Plus a negative will work just as well. But you notice that these do not change. It's the plus and the minus here. Keywords to look for when you're talking about arithmetic recurrence relations. Linear growth or decay, straight line, flat rate depreciation you're looking for. Unit cost depreciation, things that are going down or up or down by a set amount each time. That's where you're using the arithmetic sequences. For geometric, though, you're looking for the words compound interest. Again, if the investments go up, you have your recurrence relation and the rule where the R is 1 plus that. If investments go down, though, has the recurrence relation changed? Nope. But look what does change. How you work out the common ratio changes. That one goes from plus to minus. And the keywords to look for to help you pick, if it doesn't say compound interest or geometric, look for words like geometric growth or decay. Another one, reducing balance depreciation. Okay, keywords to look for there. This could be a useful slide if you want to pause and put a little table of what to look for. All right, I promised you a summary. I think that's enough for this stuff. Here comes a summary page with all the details on it. You've got your arithmetic recurrence relations and rules. You've got your geometric recurrence relations and rules. You've got your financial recurrence relations and rules for arithmetic and financial recurrence relations and rules for geometric, and how to work out the common difference using your simple interest formula or your common ratio using your compound interest. Okay? All right. Let's go get some practice. Grab your teacher, Ask any questions, ask lots of questions. This is a really important part to have for year 12. Okay, as much as you can this year, go for it.